Good morning. My name is Juan Carlos Hernandez Rios, and today I will be presenting my master's project proposal for the Mechanical Engineering Department, titled A Gesture-and-Haptic-Based Operation Framework for Improving Usability in Robotic Arm Control. This project was supervised by Professor Quintan Ventura. First, I would like to briefly introduce myself. I am a graduate of Tecnológico de Monterrey with a degree in Robotics and Digital Systems Engineering. I currently hold an M5 level in Japanese, and I'm working towards to get an M4 next summer. During my undergraduate studies, I had several international experiences. I studied at Han University, Shibata Institute of Technology, Tsinghua University, and at the National Institute of Advanced Industrial Science and Technology, or AST for short. My latest international experience was my participation at the Applied Robotics and Social Impact 2025 conference, where I presented the work I developed at the AST. This project, was called Telesign, was even selected as a finalist for Best Paper Award. Regarding my recent experience, two of the works that I contributed to were published at the 2025 ASO conference. Telesign is my first publication as first alpha. But what is Telesign? Telesign is a gesture-based teleoperation framework that enables users to control a robotic arm using American Sign Language-inspired gestures. As shown in the video, it allows human operators to perform complex manipulation tasks, such as the pegging a whole experiment. However, it had several limitations: a limited gesture recognition system, limited grip control, and limited benchmarking against other teleoperation frameworks. For my master's project, I aim to address and improve these issues. Recently, there has been important advances in gesture-based teleoperation frameworks, such as the real-time dynamic gesture framework for controlling a quadruped robot with a robotic arm. In addition, there has been important advances in gesture recognition systems. For example, a bidirectional LSTM system with mega parallel structure was used to recognize Japanese Sign Language. Most approaches on this field rely on recurrent neural network architectures or their variants. Moreover, Professor Ventura has led several related studies to human-robot interaction systems, such as the one shown in the screen. Now, as for my main proposal, my key research question is, can a multimodal teleoperation approach that integrates low-cost gesture control and haptic feedback effectively reduce physical cognitive workload, thereby improving usability and enabling model adoption across diverse user populations? My general objective for this project is to further develop Telesign into a usable and robust framework for robotic arm control, building on the foundational results from the work done at AST, as well to contribute to academic research by researching non-conventional teleoperation frameworks. To achieve this, I have four specific objectives. The first objective is to enhance Telesign gesture recognition accuracy by developing a more robust gesture recognition system using recurrent neural networks. The second objective is to integrate haptic feedback, allowing users to sense whether the robot is near a surface. The third objective is to introduce an image-based grip control, enabling more natural and flexible manipulation. And the fourth objective is to benchmark the proposed framework against conventional and emerging teleoperation approaches, such as the SpaceMouse 3D, joysticks, and VR/AR controllers, evaluating usability, workload, and overall user experience. Here, this is the proposed image-based gauntlet that I plan to develop. Second, here are two of the new main functionalities that I want to integrate on the new Telesign. First is to control the gripper's openness according to hand rotation, measured by an image sensor. This will enable a more gradual and flexible grip control. The second is to provide vibration alerts when the robot is near a surface, enhancing awareness during teleoperation. Here is a summary of the proposed system. This design shows how the user and the real robot interact through the proposed system using the image sensor, gesture recognition, and haptic feedback. Lastly, here's the overall design of the project. As shown here, the new Telesign is based upon the foundations of the old Telesign. The old Telesign used ASACTIM and RMP flow to solve the inverse kinematics of the robot, and I want to maintain the same functionalities in the new Telesign. ASACTIM is a simulation platform for robotics, and RMP flow is a motion generation and control framework that calculates joints, velocities, and accelerations according to the robot's kinematics and dynamics models, enabling more smooth and consistent movements. From a mechanical engineering standpoint, this design highlights the control aspect of the system. This system uses closed-loop controls through the use of camera and image sensors and haptic feedback, where sensors are used to control the robot's actions in the environment, while the haptic feedback enables human operators to sense the robot's environment. This human-in-the-loop control approach will enhance safety, stability, and precision. In this new iteration of Telesign, I plan to develop an RNN-based gesture recognition with media parameters action system alongside image readings and haptic feedback modules, which together will enhance the usability and mechanical responsiveness of Telesign. The expected contributions of this project are to, first, overall, a design that promotes accessibility, making the operation more approachable by people with auditory or speech disabilities or people with a much prior technical experience. The second contribution will be that this new iteration of Telesign will be one of the few teleoperation frameworks to include a systematic usability measurement. And the third is the new gripper controller using flexible image-based commands. First, I would like to clarify that I want to compare this new iteration of Telesign against two other teleoperation frameworks. First will be a standard teleoperation approach, the SpaceMouse 3D, which has been a staple in teleoperation research. The second is an emerging VR teleoperation approach, which has been increasing in popularity in recent years. As well, I would like to provide a baseline for comparison for the new Telesign results. First, I would like that the new Telesign will have a very sustainable usability scores than the old Telesign in SpaceMaster 3D, and as well, I want the new Telesign to have a lower mental demand and lower effort metrics compared to the old Telesign. The first stage of the research methodology will be a simulation-based pilot study, where at least 5 participants, ideally 8, will perform pick-and-place experiments in a gazebo environment. This will allow to recognize major and minor problems for further improvements. The second stage will be a real-world trial simulation study, where at least 15 participants from the target users populations will perform complex manipulation tasks, such as painting a hole, erase a whiteboard, etc. This will allow a more objective comparison between Telesign and the other frameworks with tired people. The data collected will be through pre-interviews, objective metrics such as the task completion times, error rates, and success ratios, and subjective evaluations, for example, system usability scale and NASA TLS. Lastly, post-experiment interviews will provide qualitative insights. The expected challenges of this project will be first, and the most significant challenge is to perform the user study design with target populations. The second will be to perform the system iteration of a new and old functionalities. And lastly, is to obtain the data and train the model of the new RNN-based gesture recognition system. Here is the project time. First, the first year will be focused on building the first prototype and performing the pilot study. The second year will be focused on implementing the improvements to the first prototype, recruiting participants for the user story, and performing the user story, culminating in the net analysis and finishing the master thesis. That will be all. Thank you so much for your attention.